Hi, in this paper, my co-authors and I provide a framework that allows one to derive decidability results for synchronizability. FIFO systems are ubiquitous these days, with applications in communication protocols, session types, verifying concurrent programs, and so on. However, for the general model, the boundedness problem is undecidable. This leads us to study variants of the boundedness property which are decidable. Synchronizability is one such notion, which roughly states that every execution can be rescheduled such that it meets certain criteria, for example, a channel bound. There are various similar definitions in the literature. For example, that accepting executions are reordered into a bounded execution. Send projections could be equivalent to that of a rendezvous. Or if every MSC admits a linearization that can be divided into certain bounded blocks. But what about the inclusion into these classes? This is where our framework comes in. It's based on MSO logic and bounded special tree width. Given a class of MSCs, if they are MSO definable and have bounded special tree width, then our result is that there is a decidable inclusion. Using this framework, we have been able to decide the inclusion to various classes of MSCs, both for the peer-to-peer and the mailbox model. To know more about how this works, come listen to our ConcurB talk. See you there.
I am going to show you how we can use guard automata to verify distributed algorithm. This work was done by myself, Bastien Thomas, as well as Nathalie Bertrand and Joseph Wider. So the type of algorithm we want to verify are threshold-based distributed algorithm. They have several characteristics. They are parameterized, meaning that they are run by an arbitrary number of processes. They are non-deterministic. This non-determinism can be caused by Byzantine fault, for example. They can be either synchronous or asynchronous. And finally, they consist of unboundedly many rounds, which makes the verification procedure harder. In order to verify this system, we went through several abstraction steps from the most concrete or the closest to the semantic of distributed algorithm on the upper left to the most abstract on the lower left. And using this abstraction, we managed to end up with the valuation on infinitely many formulas. This valuation can then be encoded in the language of an automaton. And with such a system, we can perform model checking using the usual tools and therefore manage to prove both safety and liveness properties.